Yes, so hello everyone. Good afternoon. As said, my name is Marius, and I'm leading a data science team at Diagnostics in Rotkreuz, Zug. So today I'm going to walk you through some of the technologies we're using in our team, but they're also quite popular across the community. And I will focus on unsupervised learning. But first, let's start with supervised learning, which I'm sure that everybody here is quite familiar with, which has been also the most successful flavor of machine learning out there. So in order to do supervised learning, you need a couple of things. One of them is that you need to have several, if not too many, pairs of inputs and desired outputs or expected outputs. And then you also need to have in the middle a model that learns this association, this function in the end, because this is a mathematical function. And of course here, I just gave an example with some images as input, and these are histopathological images. And then in the output we have some, for example, a binary flag, cancer or healthy. But this could be almost anything, actually, and we have a very wide variety of data that we're currently dealing with. So we work with images including histopathological and radiological text that could be structured or unstructured, usually unstructured if you're talking about clinical notes. Could be time series from different sensors and medical instruments, genomics, which in the end they are kind of strings. Proteomics, and also tabular data, the traditional good old tabular data, which, as a parenthesis here, they're a little bit special in the sense that they're usually quite strong features, so you don't really need to learn representations of them. They are representations themselves, so they're usually quite correlated strongly with the outcome. So you can use them straight as your feature vector. So now the good news is that over the past few years, or if not decades, we're seeing more and more data accumulating. So we're getting access to more and more data, and also more multimodal data, which is great. But at the same time, that's not really the case for annotated data. It's really hard to find labels, and especially in this area, in healthcare, because it's not like ImageNet where you ask, any human could annotate if there's a cat or a dog, but here, if you want to annotate this kind of medical images, it's very hard. You need to have, there are very few experts out there. Their time is very expensive, and sometimes the annotations we ask them for, they are not really part of their daily clinical practice, so they need to reserve extra time for that. So the question that I will try to entertain here is, what do you do if you don't have annotations? What do you do if you just have some data but no labels, or you have very limited labels? So let's start from the limited annotations case. Well, what most of the people do nowadays is transfer learning. And this generally works pretty well, given some assumptions. So transfer learning means that you take a pre-trained model from a relatively similar field. Of course, you need to make sure that you have the same input modality, like images, for example. So you pre-train it on this other data set, and then you transfer the model to your own downstream task, and you usually fine-tune it. Fine-tune it, I mean, again, there are a few different ways to do it. You could either freeze the model and train the last layer, or you can train the whole model, or you could train the first layers less and the last more. You may want to do one or the other depending on your use case, but most of the times it works pretty well. And it works even if you don't have, even if you have just very few annotated cases. Then another interesting question here is, can you use unlabeled data? Because most of the times you may have, 1,000 annotated images and maybe 10,000 non-annotated images. And the answer is usually yes. You can also exploit this data with what we call semi-supervised learning, or semi-supervised fine-tuning in this case. So you can use these images or whatever data points you have with an additional loss, so you add one more term in your loss in your objective, then the question is how can you do that since you don't have labels for those, where one easy way to think of is that you can generate pseudo labels with the current model you have at each epoch, at each iteration, and then you learn a little bit from this non-annotated data. Of course, that's not going to give you a huge boost in the performance. It may give you 1 or 2%, but it's for free because that's more data that you already have, so why not use it? Then what do you do if you have weak annotations? And first of all, let's discuss what is weak annotations, because it's a little bit of a fuzzy term. So weak in general means that your annotations are imprecise in some sense, they're problematic in some sense. So it may mean that they are too noisy, may mean that you just have annotations for only the positives or only the negatives or something like this. But in this context here, in digital pathology, weak labels usually means that your labels are on a different level than your model. So for example, here we have these whole slide images, which are huge. They are like many tens of thousands of pixels by many tens of thousands. So of course you cannot use one single model to describe all of them. So what you usually do is that you cut some patches, some tiles from them, and then you think of your sample of the whole slide image as a bag of things, a bag of instances. And then each tile is an instance. And yeah, the assumption we usually make in this multi-instance learning approach is that even one positive instance can make the whole bag positive. So even if one little tile there is cancer, you can say that the whole slide image is also cancerous. So now the question is, how do you bridge the gap between your model that can only describe the small tile with your labels that are global for the whole slide image? So yeah, what you usually do, as I said, is that you describe these little patches, and then you come up with some scores or either embeddings, and then you need some kind of pooling technique. So that's what MIL is actually about, is the different pooling techniques that you can use to aggregate the information, the local information, into global. And there are a few approaches to do that. So if you have scores, for example, you could try to use a simple MLP, multi-layer perceptron, a simple dense network. But that's probably not going to work very well because this does not really comply with this permutation invariant sense of the bug. Because in a bug, you don't really have an order of the different things, of the different tiles. Maybe a better approach is to use an average pooling. But then average pooling is, of course, order invariant, permutation invariant, but it's going to put the same weight to all of your tiles there. So this does not exploit the assumption that even one or two or just a few tiles, a few positive tiles can make the entire bag positive. So maybe a better choice here is to use max pooling, and this has been traditionally very popular. But at the same time, this also drops some information because, yeah, maybe one tile can make the whole thing positive, but maybe you have two or three. You don't want to miss this information. This can increase the certainty of your classification. Anyway, nowadays, most of the people use, instead of scores, they do the pooling at the embedding level. And then there you can do much more. So in most of the approaches, you use some kind of attention mechanism that decides which embeddings from which tiles are going to go forward in this weighted sum in the end, because that's what it is. But so now what do you do if you don't have any annotations? Well, if you don't have any annotations and you still have some pre-trained model, then you can still use this to do feature extraction, and then you have some representation for each of your images or text or whatever you have, and then you can use traditional unsupervised techniques like clustering, dimensionality reduction to visualize and explore your data. Or you can do anomaly detection, for example, which is something that has been proven very useful in practice in many business use cases. But what if you don't have any pre-trained model? Because sometimes you may be working on a niche area where you cannot really find an appropriate pre-trained model. Well, in this case, you should consider self-supervised learning. And in this paradigm, instead of using another task and transferring the knowledge, you come up with your own task. But you just need a task that is first easy to generate labels for, and then it's challenging enough, so you force your network to learn some interesting and useful representations, and then you do knowledge transfer again. Then I'll try to categorize some of the techniques that have been proposed recently, although this is a very active field of research, and it's quite difficult to categorize the techniques. I believe they live on a continuum, but I'll try anyway. So the first is what I call predictive here. And the idea is quite simple. So you use some kind of image transformation, if we're talking about images. For example, you rotate randomly your image. And you can do that as many times as you want. You can generate billions of data in this way. And then you ask your model to predict the rotation. So this way, you exploit all these great tools we have from supervised learning, but in an unsupervised setting, because you just generated these labels. And this way, the model will be forced to learn some actual features, like, for example, anatomical features, to decide whether there is a flip or a rotation or something like this. Of course, as you can tell, that's not something you can do with histopathological images, because they don't have a predefined orientation. So yeah, what I'm hinting at here is that you need some kind of domain knowledge to pick the right transformation to train this kind of models. So in the third example, we have this jigsaw puzzle where you cut patches, like 9 patches, for example, from your image here, you shuffle them around, and then you ask your model to find the right permutation of the patches. Then in the second category, we have the contrastive methods. This is maybe the most popular method at the moment. And the idea goes as follows. So you take one image, and then you create 2 views of this image. This can be with 2 different transformations, for example, or augmentations, as we call them. But you need to make sure that this transformation does not destroy the image, that it preserves the semantics of the image. And then you think of these 2 as positives, as a positive pair. And then you also have a random image that you pick as a negative. Then you ask your model to generate embeddings, representations for those. And you also ask your model to make the embeddings of the positives closer together and the embeddings of the negatives farther apart. So in this way, you make your model, you ask your model to learn to be invariant in these augmentations, in these transformations. And this works pretty well. Of course, there are other ways to do it. Nowadays, you use many more positives and negatives in your bats, and then other more complicated objectives. And instead of transformations, maybe, for example, you can assume that the positives come from the same slide, or the same slice, or the same patient, and the negatives come from another patient. So you can make many assumptions here, depending on your actual downstream task. And the third category of approaches is what I call generative, where in this case, the output is of the same type with the input. So the first is the standard autoencoder, where you have some images, for example, and you're trying to reconstruct the images in the output. Of course, you need to make sure you have an information bottleneck in the middle. So the model cannot just simply copy the input to the output. It is forced to compress, because that's what these models do. They compress your data, so they learn some interesting representations this way. Yeah, unfortunately, this model doesn't work that well in practice in most applications. It may work for some anomaly detection use cases, for example. But the second one, the mask autoencoder, works pretty well. So what you do here is that you mask out some parts of your data, of your input, and then you ask your model to reconstruct those. So and this is usually applied with a VIT, a vision transformer, as a backbone, which it seems that it fits very well this self-supervised learning paradigm. And if you think about it, this is very, very similar to the way that the BERT language model is trained. Similar architecture of the model, similar training approach. So that's the three main categories, but nowadays most of the modern SSL, self-supervised learning approaches, they use a combination of the previous approaches. They usually have like some losses coming from the generative area and some loss coming from the contrastive, like for example the Dino V2 technique. And yeah, currently they work pretty well and they are very generic. And what is interesting is, in some cases and in some sense, this self-supervised, self-supervision is more accurate than actual human supervision because it makes less assumptions. Like, for example, if you ask humans to annotate regions around cancer, even if you pick the best experts in the world, they're going to do it slightly differently. So you're going to have some inconsistencies in your supervision. But this kind of self-supervision is much more reliable. The assumptions you make are less. So in the end, they're also less biased, usually. And then to come to my last slide, what do you do if you have multimodal data? And this links back to my first slide, where I was talking about having many different modalities matched to each other. And yeah, as said, it's hard to find annotated data, but it's getting easier and easier to get big, non-annotated, but multimodal data. So in this case, for example, this is a paper, this is a model called CLIP. It's based on CLIP, which is a model developed by OpenAI. And it trains jointly text and image embeddings. So what you need to have here is pairs of images and text. This could be coming, for example, from electronic health records. But in this case, they got the data from the web, from Twitter. And of course, this data may be noisy, but it's a lot. And it turns out that these multimodal data work very well as for supervising each other. So you can think of the text as label for the images, and the images as labels for the text. So you can train both of them at the same time. And you can start with some pre-trained image and text encoders, and then you keep training them so they generate embeddings that are close for the matched pairs, and they're farther apart for the non-matched pairs, like here. So yeah, I personally believe that the future of machine learning is going to be unsupervised, and I think that this kind of multimodal self-supervised approach is a very promising direction. And that's all from my side.